Is it fine to start now?
Yes, Dr. Saab, please start. Please go ahead.
Yeah, yeah, thank you. So, everyone, please feel free to put your questions, queries, anything on the chat box. So, I think many of you are already you already have seen me several times. This is probably 11th, or if you include the AP series, also probably more than that. Many courses I have been part of, fortunately and humbly. So. Often I covered in the previous QTs on mathematical aspects, mostly probabilistic interpretations of quantum mechanics, quantum computing, as well as the linear algebraic way of understanding quantum gates, circuits, operations, algorithms, etc. I got an opportunity to take 6 hours in this course as well, in this solid state QT-10, the quantum computing with the solid state physics coherence part. In the last QT, you have been those who attended the QT-09. You have seen the angle of the demonstration was towards the computer science people mainly, but it was open to all. So hence you have seen the complexity theoretic aspects mostly. So as I get an opportunity to cover again the very fundamental topics, and many of you probably are seeing these subjects repeatedly, this gate 0, gate 1, gate operation, circuits, various quantum gates, and the same thing. But I take an opportunity to visit the subject from the theme, like the solid state, and hence some of the things I think already that is well taught in this course, and probably I am taking the last two lectures, and as an industry person, so there will be some flavor from the industry side, some flavor from theoretical side, and some of the things are from the textbooks, and some of the things are from my experience. So all at the things, and because my background bachelor's was in electronics and communication engineering, later I slowly I went towards the algorithm side from my master's and PhD. So it gave me an opportunity to go back to my UG days and basically interact with oscillator circuits, those things, and we'll interact those things once again. Thank you very much. So, first lecture today, and tomorrow will be the second lecture. So, as it is said that quantum mechanics revisit, and I think many of you are from physics background, so no need to explain each and every detail of quantum mechanics that is taught. We will only take the very surface level thing, and probably the interesting mathematical aspects which are required for the quantum computing and information theoretic side. So what are the textbooks required for this? So many times I asked this question. So these are some of the reference textbooks for this course, particularly if you see those who are basically coming from physics, so they already know many physics books names. But those who started from other than physics background, from computer science, from electronics, electrical, various biotechnology, and other departments. So there is an scope for you to revisit some of the physics background so that you can appreciate the theory behind the computation, right? Or understanding the mechanics of the computations, right? For that, there are two standard and very good textbooks. One is the Feynman lecture series, this particular book. And this book basically has a description on multiple topics based on the lectures basically Feynman had in his classes. And this is basically written by some of the attendees. And this is a standard, very standard textbooks. I'll suggest those who are interested to research, basically the scholars, right, and as well as the faculty members who are interested in this subject very much. And I think this is the starting book everybody should consider, the Quantum Mechanics Introduction by David Griffith. Why it is so important? Because the language of this book is more on the linear algebra, so you don't need to worry about the uh, I mean the physical description in terms of the calculus language. For example, the Sakurai book, if you look at, right? So it starts with the Green's functions and all. So sometimes you may feel difficulty to understand the book. in from that angle, this particular book Griffith starts with the very simple. If you know the vectors and matrices and their relations on the vector space, right? So those under the 10 plus 2 level and undergrad level mathematics will help you to understand this particular book, Quantum Mechanics by Griffith. So this is, I think, one of the most easy and most important bachelor's level, UG level textbook for anyone. Now, those who are even basically just directly want to start the circuitry part or the quantum computing part and still need another reference book to understand some of the important physical understanding of the quantum mechanics, specifically the operator picture that I will be covering today are mostly from this particular book. This is another book is called the Basic Quantum Mechanics by Tambakis. And well, there is the physical intuition is quite less, but the mathematical description is quite good in this particular book. And you can have a look, especially the both the Schrodinger picture as well as the Heisenberg picture are basically well described in this particular book. And now, this particular book, that is Quantum Computation and Quantum Information, we sometimes call this particular book as the so it's like a Bible in quantum computing. Okay, so it's like the starting book in quantum computing, but it requires you to have some knowledge, some understanding of the computation theory and some understanding of the information theory. So those who already have some bachelor's in electronics or communication theory or in computer science, and just want to start want to master this topic and starting a book, for them this particular book is excellent one, this by Nelson and Chuang. And those who are interested in the information theoretic part, specifically understanding the quantum communication principle. So tomorrow I'll be discussing on some of the important aspects in the quantum communication theory, like no cloning theorem, the teleportation theorem, right? So those things for which this is the reference book, and this is a very standard book, but more major focus is on the information. So both the Shannon classical Shannon classical communications theory and its interface with the quantum Shannon theory or the quantum communication theory, both aspects are well described. And on the modern perspective, like the quantum internet, quantum informations, various very modern topics. You can have a look to this very recent book in Springer, The Theoretical Foundation of Quantum Information Processing and Communication, by Bruning. So and others. So these are some of the important reference book I would suggest for basically you those I think many of you will be teaching in your classes, so this can be referred to the students. Well, um, so I'm dividing my particular 3 hour sessions into two part. So basically, first part will be on the mechanic side and the hardware side, and the second part will be on the computation side, and as well as the Qiskit demonstration. Although I won't show the programming in this particular course, but in general, the mathematical description will be there. So when we say review of quantum mechanics, right? So there is a huge theory development in last 100 to 100 more than 120 years, right? And there are many people who developed this theory, right? And some of their names I just put down in some categorical fashion to understand, right? So first is, for example, this the first phases we know from our school books, right? Sorry, say the origin of quantum theory in those even who are not coming from physics background, right? So still they have, like, they know all these phases. For example, starting with Max Planck, the radiation theory, right? The black body radiation explanation of that. So because when Max Planck starts his studies, graduation studies, and his professor said, okay, physics is complete, because he said from his professor name is Philip von Joly, and he said in 1878 that physics is almost complete, right? And it is highly developed. There is nothing remaining to do as such, because there was huge development in thermodynamics, And there was a lot of things. Only there were some experiments which basically could not be explained by the classical theory. For example, the black body. Max Planck took this initially he started with the study of energy, thermodynamics, and all, and later he invented the entire theory of quantum physics, basically the Planck's quantum physics, and this subject started from there and continued by many people. Like for example, in the initial days by the photoelectric effect study of the photoelectric effect by Albert Einstein and use of the Max Planck, the discrete description of the energy coefficients. Also co-developed by Niels Bohr, right? Bohr's atomic model. Then there was a lot of development, and slowly that every matter has an basically representation of wave description, right? By Louis de Broglie. And then basically experimental studies were done by many people, and some of them were Stern and Gertschlet. And this experiment we know, the basically sending certain basically silver atoms within the magnetic channel, right? And how they basically how you detect those particular atoms, right? And of course, the SN Bose, the Bose-Einstein condensate, right? The statistical description of the many particles, right? And this is what we have studied. On the when we study the quantum computing, basically, you will be seeing various description of the operators, right? And some of the operators are chosen from wave mechanics. Some of the mathematical descriptions are taken from matrix mechanics, and some of the things were taken from the relativistic quantum computations. Although this part actually we do not consider as such, but for example, the wave mechanics like the Schrodinger equations, like to understand the time propagations in a quantum circuits, right? And the measurement rule by Bond's rule, right? How do we measure a particular quantum state? Then the particularly when we devise the wave mechanics part, the when you describe the Schrodinger equation, so there is a relation from Louis de Broglie to Schrodinger's equation. So he picked up the wave particle duality principle of quantum mechanics. But Max Born has the wave mechanics description from the statistical interpretation, so which were developed very independently than the wave mechanics. And in this particular part, there were many people. Some of them were like Heisenberg, who gave a very good like uncertainty principle. Statistical basically came from the statistical commutation and anti-commutation principle. Those mathematical description I'll come, as well as Max Born, uh, the Pascal Jordan, Pauli, von Neumann. So von Neumann later came towards the information theoretic description of the quantum mechanics. And Pauli will come basically some of the matrix descriptions and all in terms of the any quantum gate operators, in terms of the Pauli operators and all will come. And Paul Dirac, although he is quite famous, he is very famous in relativistic quantum physics, but we will call his name because we'll represent the entire quantum computation representation in Dirac notation form, or we call Kate and Bra notation to honor his name. So these are some of the faces. Basically, if you are interested to understand the history, you can just go to the Wikipedia or anywhere in the internet, and there are a lot of interesting studies which will inspire you to study the quantum computing. So let's start with the two particular case. One is because in quantum mechanics, everything is described in terms of wave function. Today, not only wave function, we'll try to understand quantum mechanics in terms of another language. One is called the state vector representation. State vector representation. And another representation we'll do with density matrix representation. So of course, those who will be studying the physics book, the language will be in terms of the wave functions. And the entire quantum postulates you need to study with the help of, because it's a function, f of x is a continued valued, basically mathematical object. So everything we have to study with calculus, basically. Calculus, okay, like integration and differentiation. On the other side, although for the discrete representation also the calculus validates, But for the like geometrical interpretation of the things, the suitable method is the state vector representations, which are also easy for the computation purpose, how we represent information in the basically vector space. And also there is another description, specifically if you consider the noisy versions or the composite versions of various quantum configurations on the density matrix representation. So I'll cover these three part together in this session. So three different language of representing the quantum mechanics. So let's take a wave function f of x. It's some wave function. So typically physicists prefer to write in psi of x. It is also it's basically a function of space and time. When you say it's a physical like space, like the space you can visualize, it's R3, right? So and if it is like it can be any n-dimensional way you can represent the wave function, but in general it's represented in three-dimensional space and time variable, right? So two particular, like let's take two particular example of wave function. One is a Gaussian wave packet, and another thing is a plane wave packet. And they why I particularly take this two particular thing. There is a lot of story. It won't be possible to cover the story in this 1 hour thing, but um, so so for example, this Gaussian wave packet, if you see the position versus the x versus f of x plot, right? X versus f of x, domain versus the range plot, right? Or the particular domain versus the functional mapping plot, right? So you can see that in this particular region, right, of the particular domain x, I have the maximum concentrated energy of that particular wave packets, right? So this is the maximum energy concentrated here. And outside this, suppose this is my x1 and x1 and x2. So integration, that getting this wave function psi x dx from x1 to x2 is maximum. It's the maximum energy of the functions, right? So there is a highly probability within delta x to get the maximum energy of this particular wave functions, right? So, and in the other case, if you see, I cannot define a delta x, a small delta x, within which the maximum energy concentrated. So my energy is flat in this particular region, right? So now if you take the Fourier transform of this particular thing, for example, it's written in the exponential or trigonometric form, and this is the Gaussian wave packet. So if you take the Fourier transform of these particular things, you will see a flat, particularly the basically frequency versus or omega versus, you can plot omega versus the psi of omega, right? So you will see almost flat. So why I take frequency? Because frequency has a relation with the momentum, right? And so momentum you can write in terms of the frequency or the angular frequency component, right? And although the position is quite certain within delta x, but now the wave function in the frequency domain is quite flat with respect to the momentum domain, right? Similarly, wave function has quite opposite. If you have this kind of where basically wave function is quite flat in x, that I cannot find a small delta within which the energy is concentrated, right? That means there is highly uncertain within position, right? Uncertain in position. Now, if I take the Fourier transform of this, if it is just say, for example, take a sinusoidal case, so you will get the frequency component like this, frequency omega versus the psi of omega. So it has quite certainty in the frequency domain, right? So these two are opposite particular case, plane wave and Gaussian wave packets, where you can clearly visualize that if I have a certainty in position, I have uncertainty in momentum. If I have certainty in position, uncertainty in position, I have certainty in momentum. So we'll look this later. We'll look into this particular thing later on the uncertainty principle, right? These two particular complicated cases. So these two are particular web packets which we'll be using again and again for various purposes. Now, quantum operators. So quantum operators, what is operator? Operator is some object that you operate on the wave function and get back certain quantity, right? And it has certain mathematical properties. So typically, in our particular computation case in quantum computers, when we'll be doing on algorithm, these are simply matrices. Okay, simply matrices with certain properties, whether it will be unitary matrix or Hermitian matrix. So those properties I'll come and why these properties are required. So in general, what is the definition of an operator in our quantum mechanics is that operator is a mathematical object. If you apply that particular operator to a particular wave function, you'll get back to the particular quantity A. If you apply A hat, this is an operator and operator, and then you get back a quantity, right? If you apply this particular thing, you get back a quantity out of this. This particular equation, you can now easily write it as Ax equals to lambda x, right? So this basically so when you basically write this particular mathematical equation in terms of A equals to lambda x, only if for some x x vector non equal to 0, right? That is called an eigenvector. And I have a normal matrix A that I apply on that particular wave function or the eigenvector basically in this particular case. And I get back a scalar enhanced scaling of that particular vector. That means if I have a vector x like this, and if I apply a matrix on this particular operator, right, A, so I'll be getting a scaled version of this particular vector, that is A times x bar, right? So that is just tracing. Either it can be less or it can be more, but the direction theta will be constant. There will be no change in the direction, only scalar stretching of this particular vector, right? And now this particular case, when like all the physical quantities in physics, they are real quantity, right? For example, position, momentum, energy, all these are real quantity. And I will have the eigenvalues to be real if and only if A equals to A star. That is basically Hermitian operator, right? Hermitian matrix or Hermitian operator. So matrix only if you write wave function in terms of vector, then we'll come to the matrix part, right? Okay. So what I define is that an operator should be in physics sense, it's a Hermitian matrix or it's a Hermitian basically operator, which I apply to a wave function and I get back my desired quantity. For example, a particular physical quantity is x, right? Now, what is the corresponding mathematical operator? X had, whose eigenvalue is x, okay? When I apply the x hat. For example, the momentum operator, basically momentum is written as h bar k. K is the wave number and h bar is the Planck constant. This is particularly the momentum p. So how can I get this momentum out of a wave function? So I have to apply a momentum operator on this wave function psi. Then only I'll be getting a particular momentum scalar quantity times psi, right? So then I have a corresponding operator, basically Hermitian matrix or a particular in when I represent this as a eigenvector form, then this operator is basically a Hermitian matrix out of it. So every physical quantity has a corresponding operator. So let's take some example to understand this. Say I consider a plane wave function like this, and I have my position operator x hat equals to x. Now, if I apply the x hat onto the state psi x comma t, so x x had applied on psi comma t is basically x of psi x comma t, and I get back basically if I apply x on the wave function, so x time the exact wave function I can write, so x become the eigenvalue and x hat is the basically corresponding operator. So this is a very trivial example. It's a bit difficult to understand. Let's take the position operator, momentum operator, for example. So the momentum operator is defined as I h bar del x. Okay, and if you apply the p hat on the particular wave function psi xt, say it's particularly plane wave. Okay, So you simply take the derivative, partial derivative with in terms of x, right? So I h bar, just you applied this particular operator on this particular wave function, and you'll be getting I h bar. A is constant. You just take the derivative with respect to x, and ultimately you will be seeing that it is h bar k times psi of x comma t. So that means h bar k is my lambda eigenvalue, right? And that is the quantity I call momentum. So momentum is the eigenvalue of the momentum operator, where momentum operator is I h bar del del x. So every physical quantity has a operator description. So this is an important operator, energy operator, which we used left and right in quantum computing, quantum mechanics. So the energy operator, also known as the Hamiltonian operator, is written as I h bar del del t. So if you apply the Hamiltonian operator on the wave function psi xt, say you have taken the same plane wave function, and you just need to do the derivative in terms of t. Now, in the previous description, we have defined the momentum operator in terms of this particular del del x, right? So del del x is the derivative with respect to x, means space. So it's a p is compatible with space. That means p has defined in terms of space, whereas the energy is defined in terms of time. So that's why later you will see that momentum has a certain uncertainty. I'll come to later that momentum and position, they have some sort of uncertainty, and similarly energy and time has certain uncertainty. So I'll come this part bit later, but just keeping from the definition to those relations, I'll come back. So the definition of energy operator or the Hamiltonian operator is I h bar del del t, partial derivative with respect to time. And if you take the partial derivative with respect to time, you'll get that basically h bar is here. So I and I will be -1, and there is another minus, so it will be ultimately +1. Omega will be outside, so h bar omega. And rest of the part is the definition of psi, that is the wave functions, plane wave. So I got h hat psi equals to h bar omega psi, right? So this is my lambda. That means this is the eigenvalue. Energy is the eigenvalue of the Hamiltonian operator. So h bar omega, right? This is my energy quantity E, right? So h bar omega means h bar omega equals to 2 pi f, right? So basically, I get h bar means h by 2 pi again, and 2 pi f. So it is equals to hf. So we know that energy equals to h nu, right? So this is the equation we learned from Max Planck, right? Max Planck, where nu equals to a frequency, right? And h is the Planck's constant. So this is how things are related, right? And and this is the operator picture. Like any physical quantity, it has a corresponding mathematical operator, right? Now, why I cover these particular things, there are of course reason, right? I am not covering the physical intuition behind this. So those who are interested to understand how the, for example, how Schrodinger equation was developed, right, in 1925-26, how it was developed. So you'll see that already the equation was there, but there was something missing. If you see the left hand side and right hand side of the Schrodinger equation, left hand side there is an imaginary part, and right hand side it is a real part. So by just ordinarily looking at the equations, for example, I h del del t psi t, right, equals to h of psi t. And h can be your kinetic energy plus potential energy. And left hand side, there is an imaginary part, right? And right hand side, that is almost real. Suppose psi x, you don't consider it's a complex number or whatever way, right? So there are like there was certain mathematical incompatibility unless you put h equals to h hat, right? There is an operator description of h. Then immediately once you put the h hat part, then h in the h definition, actually imaginary part is coming. Now psi t, this particular case you can define in terms of say particular plane wave or whatever wave you want to do. So there are actually reason to to basically have this kind of operator description of the things in the development of physics. Okay. And another reason is there, that was the reason from the physics side. There is another reason in the computer science part, that is, um, so basically, when we are interested, suppose there is an wave function description of, say, particular molecule, say NaCl, right? Sodium chloride. What is the minimum ground state energy of this particular molecule, right? Or you want to study the H2O, hydrogen, basically, H2O, right? So in this particular water molecule, what is the minimum energy needed to particularly dissociate oxygen and hydrogen from water molecule, right? So these kind of studies, if you want to answer, right? So you have a wave function description of that particular molecule or individual atom, say it is high, okay? Now, in order to compute certain quantity, say lambda, right? Lambda can be eigenvalue or whatever it is. So you need to basically operate on it. Whatever quantity you want to calculate, that is an eigenvalue of an operator, right? So corresponding operator is A. So that A has a circuit description. If it is a matrix, so I should be able to design a circuit for this particular A, right? So I'll come about the circuit description part a bit later, second part of this session. Now let's come to the definition. Okay. So I um, talked about the Paul Dirac, and Paul Dirac, we write the entire Dirac notation in his name. Is there any problem with the audio? Like, am I audible? So in general, all my previous classes I used to do in pen and paper method, writing everything. But because the topic is quite broad, I thought to make the PPT. If you have any trouble, please stop me. I'll explain each and every terminologies. Can anyone confirm that it's audible, right?
Yes, sir, it is audible.
Yeah, thank you. Direct notation. Like we have numbers, right? In classical computer theory, we have certain, say, a particular set of numbers x, and x has certain components, say x1, x2, x3, right? Dot 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 x sum n. Um, so now, and often we start with x0, for example, right? So xn minus 1. So this is some Rn, right? So we have certain numbers, right? And we want to do certain computation on this number. We can add them, we can multiply them, we can do certain mathematical transformation on them. We can do certain machine learning stuff, cluster them or classify those component of the numbers, or identify, say, for example, what is the maximum of this particular array. So there are a lot of computation we do once we have certain numbers, and we prefer to represent numbers in terms of vectors, right? Or in computer, we often write them as tuple or list, right? So when I say vectors, and immediately I need to ask the question whether it's a column vector or a row vector, right? Similarly, when we represent the wave function in terms of discretized form, right, we have vector representation, and we have two types of vector representation. One is the column vector representation. We say ket notation, ktex, where you write all the component x0, x1 to xn minus 1 as a column vector. And another representation is the bra representation. And together, this is known as the bracket representation. So which is a basically row vector, right? Row vector representation. So immediately a column vector is C complex n cross 1, and a particular row vector is 1 cross n complex vector, right? So this is a very simple definition of bra and ket, that is the column vector and row vector. And when I say certain quantity as a vector, so where they belong, where they stay, right? What is their kingdom? So they basically reside in a particular space called vector space. And when they reside in a vector space, there are certain rules, regulations in the vector space. Often we study in the vector, like the properties of vector space. I'm not writing all those properties, right? So there is something called the scalar multiplication. So closure under scalar additions, as well as basically the scalar multiplication and the two important property, and the existence of the zero vector and other things, right? So there are definition of that particular space. Now, this vector space, there is a special vector space in quantum that is we called Hilbert space, which has two particular property. Of course, a Hilbert space is a vector space. That means it obeys all the properties of vector space. That means if I have two vectors, say x1, x and y, these are two particular vectors which represent the quantum state. Then there are linear combinations. That means constant time x plus another constant time y that should also belongs to that same vector space, right? So that means the superposition is possible or linear combination is possible. So if I have two valid quantum state x and y, then their linear combination C1x plus C2y is also another valid quantum state, right? This is the first property. And the second property is the inner product property. What is the inner product property? Is that there exists an inner product, basically which gives basically H cross H to another basically C value that satisfies the following properties. That means inner product gives a scalar quantity, complex scalar quantity. It can be a real scalar quantity. It can be some basically scalar quantity C. So um, so basically, it's defined in this way. So it should satisfy the linearity property. So the definition is like we'll come back the inner product, how to calculate the inner product in quantum machine and all. I'll come back. But in general, it has to satisfy the linearity property, conjugate symmetry property, and positive definiteness property, right? If these properties are satisfied, we say it's a inner product space is valid. And if it is additionally, if it is a vector space, then with these two properties, we say that the particular vector space for quantum computing, we say it's a Hilbert space, right? And there is a third property, often we say the completeness property, which basically will come back in the quantum postulate part, that H has to be a complete metric space with respect to the norm induced by the inner product, where norm is defined by square root of the inner product x comma x. So we'll come back to this term completeness from various angles, even from the measurement. If you have multiple measurement operator, and then basically some of the measurement operator gives the identity matrix, that is also another definition of completeness. I'll come back. More on the Dirac notation. So the inner product I was saying. So if you have two particular quantum states, say x and y, their inner product is defined as x1 star conjugation yi. So xj star yj, where sum over j, basically individual component wise multiplication and summation of all the components, right? Of course, like the first component, you have to take the complex conjugations, right? In these particular multiplications, then you say this particular mathematical quantity as a inner product. For example, if you have say element like 2, 3 plus j and 5, and if you this is suppose say ket x and ket y equals to say 5, so I'm dividing it with some a to normalize, right? And 5 say 7 minus j and 6 and normalized with b, because for every valid quantum state it has to be normalized. We'll come back to in the postulate part. So now by inner product you multiply this with this plus this particular component with this particular component, but in this case 3 plus j will become 3 minus j, okay, after complex conjugation, then multiply with this particular part plus this particular component into this particular component. So 10 plus 3 minus j into 7 minus j plus 30, right? So this is the inner product thing. And norm is the square root of that particular inner product. So all these terms are important when you have the measurement interpretation of the quantum mechanics. One of the most important part is the linear combination of basis vectors. If I have a set of n linearly vectors, E0, E1, E2, all they are basically independent vectors, they forms the basis set in say in Cn. The state vector x. So basically, in short, you can write it orthonormal basis set ONB. Okay. So if I have some set of orthonormal basis set, then I can write a vector x uniquely as a linear combination of the basis vectors. So where x is sum over certain constant Ci times the EI, where EI varies from j equals to 0 to n minus 1. That means if I have a two coordinate system, say this is ket0 is a basis vector, ket1 another basis vector, and this is my psi vector. So I can write it is as alpha times ket0 plus beta times ket1. Now, if I have more than this basis, for example, in a hypothetical picture like this, and I have four bases, say 0, 0, 0, 1, 1, 0, and 1, 1. If this is the case, and I have certain quantum state vector, say psi, now psi has four components. One is along this direction, along this direction, along this direction. So I can write psi as say C1 times 0, 0 plus C2 times 0, 1 plus C3 times 1, 0 plus C4 times 1, 1, right? So if you have such orthonormal basis sets where each of these bases basically are orthonormal to each other, they are normalized, then you can represent any quantum state in this particular basis set in this way, right? So this is like linear combinations of a particular quantum state in the basis vector. This is very fundamental, right? How you represent a quantum informations on a quantum computer. This is only possible if and only if the individual component has the inner product of delta ij. It means if you multiply this any say ket0 times ket0 inner product, it should be equals to 1, and 0 times 1, if 1 is your basis vector, it should be 0. So then only I can say ket0 and ket1 are orthonormal to each other, right? That is represented by delta ij. That means this is equals to 1 if I equals to j, else it is 0 for I not equals to j, right? And the completeness relationship is that if you form certain projectors, right, out of this, for example, if you create a projector like this 0, 0 plus 1, 1, you'll be see it is equals to identity matrix 2 cross 2. You can easily check by doing in hand. So when you have four orthonormal basis set, you should come up with a um,
Sir, your
hello.
voice is not
Uh,
audible.
yeah, sorry. Actually, it is storming in Kolkata. Electricity went, but I connected through mobile. Now, am I audible?
Yes, sir.
Yeah, so sorry. Actually, it's outside. It's storming and lightning. Sorry for this. Yeah. So if there is any disturbance, please write in the chat box so that I can understand if there is any issue in the internet or not. So this is the completeness relationship that if you create certain projectors out of the orthonormal basis set, the sum should be equals to identity matrix. This is also another definition of the completeness. Now let's come back to the quantum postulates. So because when I say the review of quantum mechanics, and without quantum postulate, I cannot move a single step, because what do we understand by postulate means minimum assumptions that is required, right? What are the basic assumptions in quantum mechanics which are required to for going further? So typically those who have like studied from the physics book, they have seen this wave function description today, and also those who studied from the quantum computing book from for example the Nelson Chuang book or quantum information theory book, at least the quantum computing book, and also Griffith. So this is the description, state vector description is there. And the third description I'm also giving today, that is mostly for the quantum information theory side, is the density metric description of the quantum postulate. Three different way to understand quantum mechanics, right? Now, what is the wave function? So first, so quantum mechanics tells about how we describe object in quantum world, how do they behave, how we can operate on them. Once we operate on them, what are the consequences, how we disturb them, right, in order to understand them, right? These all things are described in certain postulate. So first postulate is to describe the object. So the state of a quantum system is completely, just 1 second. The state of a quantum system is completely described by a complex valued wave function psi t. So this is the basic description that you don't need to describe with so many laws. Like in classical mechanics, you have certain rules, right? The kinetics or the kinematic equations, the force, right? Many other things are required to in order to describe the object dynamics and statics, right? But in quantum mechanics, you only need a wave function psi, which is a function of position and time, and it is square, at least square integrable functions, right? That is the psi r comma t. If it is even it
Sir, your voice and screen is not visible. Sir, screen is visible, but voice is not audible.
am I audible, ma'am?
Uh,
No?
yes, sir.
Yeah, sorry. Yeah. So the wave function, that is a function of space and time, it should be at least a square integrable function, and the integral basically over the space gives the value of unity. So this particular quantity, why I say unity, because there is a description of the quantum mechanics in terms of the statistics, right? So there actually has certain probability notion. So this particular quantity psi squared d3rs is basically is the probability of finding the particle in the volume element dr3t. So one of the simplest descriptions, we take a one-dimensional case, so we can write integral over x psi of x comma t square.
Sir, your voice is not audible.
So psi x is the, yeah. So if this is the psi x is the description of the wave function, am I audible?
Yes, sir, you are audible, but screen is coming and going. It's not
Yeah.
stable.
Now stable?
Uh, yes, sir.
Yeah, thanks. So if psi x is the description of the wave functions with x as the variable, now the square of this particular psi of x, that is psi square x, psi x square I should write, gives me the probability, right? Suppose from here I can write, suppose this is my square form. So this particular area in the x region, say this is a particular small region can be dx, and the whole region if I integrate, that is the area under the curve of psi square x, psi square x. So that particular area gives me the probability of finding the particular particle in the region, say x1 to x2, right? So that is the description of wave function in postulate 1. The same thing I can represent in the state vector form. So the state vector of a closed quantum system is a unit vector psi in the Hilbert space. And when I say unit vector, so that means the norm of this particular vector equals to 1, right? And and otherwise I can better write in this form the inner product psi and psi equals to 1, right? So satisfying that the inner product of psi and psi equals to 1, and the states differing only by global phase e to the power I theta psi are physically identical. So if I do particular states, say phi is another state where phi I can write e to the power I theta times psi, then this psi and phi are basically identical on the Bloch-Sphere. Okay. So this is the state vector. So in simply how I can understand, so a quantum state is just in quantum computer, it is just a unit vector. Okay, unit complex vector. That's it. Complex vector. That means this psi is belongs to, say if it is there are n elements, so this ket psi belongs to C n cross 1 n dimensional complex vector. That's it. With its norm equals to 1. There is another description called the density matrix description. So I'll define the density matrix bit later. For now, the most general, so any basically composite quantum system or any quantum system which has basically multiple realization or ensemble, there is a description called the density matrix description, where actually the most general state is described by a density matrix on the Hilbert space H, which satisfied that it is a Hermitian operator. That means psi dagger equals to psi. It is positive semi-definite. That means psi greater than equals to 0 and trace of psi equals to 1. These are the three properties of our density matrix. If a state is pure state, then the density matrix is simply the outer product of the quantum state, psi and psi outer product. With trace of rho square, this rho square, trace of rho square is known as the purity. So often we define the purity of a quantum state by rho square, and trace of rho square is a physically measurable quantity. If it is equals to 1, we say this is a pure state. And if there are many realization that I have a quantum state and this quantum state is not pure, that means it has multiple realization. There is realization 1 with probability P1. There is realization 2 with probability P2, because often you create quantum information. There are certain basically uncertainty due to temperature and other physical phenomena. And you can get multiple ensembles of the actual quantum states, say psi 1, psi 2 to psi n minus 1, multiple realization, and with multiple probability amplitudes or probability mass functions component like P1, P2, P3. That means psi has a description, psi I with probability mass functions Pi. This is called the ensemble description. Then you can define a matrix in this way, that is Pi outer product of psi I over I as a sum, you will get a matrix psi, which if the probability is uniform, that you get every individual ensemble with equal probability every time, that means that's a pure state. So you'll get back to the pure state. But in general, that may not be uniform distribution, that can be any other distribution, right? So then basically that particular state we called a mixed state. And for mixed state, basically trace of rho square is less than 1. So this is often we call the impure impure state density matrix. So this is the description of first postulate in terms of wave function, state vector, and density matrix. Till this, if you can just put it here. Next postulate. Um, Next postulate is that, okay, I define what is wave function in the first postulate in different ways. Now, um, what is an observable? I have some psi, and previously we have seen if we want to, okay, psi describes certain physical phenomena, but what to do with the physical phenomena? I need a measurable quantity, right? If there is something, I have to know, okay, whether that is good or bad, or that has certain physical notion, even computable notion. For example, what is if there is a description of certain particle, and we often want to calculate what is the distance from origin, what is the velocity, what is the acceleration, what is the mass, what is the momentum, all these physical quantity, right? And in order to find the physical quantity, I need an operator corresponding to that. I need to represent the wave functions in the eigenbasis, say A, then I'll be getting a quantity A, and there is a the same particular eigenfunction should be there, right? So this is the description we just learned previously. Now we'll see the same thing in the postulate form. So every measurable physical quantity, that means if I say how much I am happy out of an wave function description of mine, that might not be measurable, right? Possibly. But measurable quantity means that we can quantify with a measurable device, right? So every physical quantity, say quantity A. So now I earlier I wrote in the smaller A form because that's a scalar quantity. Now in this node it is written as capital A. But when typically we represent any operator, we put a head on it. This is a matrix form or operator form. But in general, in mathematics book, we try to write in a small letter for scalar and capital letter for matrix. But there are certain notational change in some places. I'll just let you know. So in this particular case, A is a scalar quantity. It is not a matrix. So every measurable physical quantity A is represented by a linear Hermitian. Hermitian means self-adjoint differential operator A hat on the wave function. For example, the position and moment of representation as x hat equals to x and p hat equals to I h bar del x. These are the operator representation, right? So the eigenvalue equation that A psi over x, if the position is x or r, A n psi x is the eigenvalues A, which are the possible measurement outcomes, only possible measurement outcomes. So the same thing that we have learned, this is the formal representation of that. In the state vector form, that is much more easier to represent, because here in this particular case, if you have an matrix, because in this particular case, you have functional representation and calculus representation, right? Calculus means the differential or integral form. Here you have the basically matrix form, that which is quite easy to understand, because many of you do machine learning stuff and nowadays data analytics, those stuff. Even if you don't do the physics formally, but at least you have the notion of data and all those things. So state vector formulations is quite easy to understand. Every observable corresponds to a Hermitian matrix, right? A hat equals to A hat star on H Hilbert space. The spectral theorem guarantees a complete orthonormal basis A with real eigenvectors, eigenvalues A n. So the same thing, but here you represent, that is, this is a matrix. These are the eigenvectors, these are the eigenvalues, and this is the eigenvector, right? So eigenvector form, or you can write in the spectral decomposition form in this way. So these are actually equivalent. This and this equation, Ax equals to lambda x. This is equivalent to write as A equals to lambda x and x outer product xx star, right? So same thing when you have multiple such eigenvalues. So A xi equals to lambda I xi. then you can write it as A equals to sum over lambda I, outer product of xi and xi, right? So this is known as the spectral decomposition theorem. And so if you expand these things, so you'll be getting the eigenvalue decomposition of a matrix. So where this term will be basically u lambda and u star, that particular thing is possible, right? So, okay, there are steps. I just did the step jump and just wrote the similarity, how it is really relevant. But this is the spectral decomposition of a Hermitian matrix A, provided A equals to A star. Okay. And the density matrix formalism is that the state is identical to the state vector case. Observable are Hermitian operators, and only their eigenvalues are measurable. The same wording are same. Just the notation is written as the expectation form. So expectation of A hat, this is the expectation computation, which is trace of the operator A hat times the row, because now instead of the psi description, we have a row description. So because rho is now is basically outer product of psi and psi, right? If it is pure state. And if it is impure, then sum over pi psi I, outer product of psi I, right? So that particular row will be here, and you'll be getting the observed quantity as the trace over A hat times rho. Okay, this is the second postulate. So you may feel a bit difficulty on the density matrix approach, because you need to be very fluent with the information theoretic stuff to understand these things clear. But I'm keeping all the three things together, right? So tomorrow things will be more clearer on the density matrix approach. So because I'll recall all this stuff tomorrow to basically cover on the information theoretic stuff. Third postulate is on the measurement side. So that means now if you have a wave function, right, and if you project it into some of the eigen basis, right, you'll be getting back to the quantity. So this is the wave function description of that. This is the most easier one. So let me give an example for simplicity. Suppose this is my quantum state psi, right? And I say my psi is alpha 0 times beta 1, which is superposition of 0 and 1. Suppose this is my ket 0 state and this is my ket 1 state, right? So what is ket 0? Ket 0 is 0 and 1 and 0 vector, 1 0 column vector, and ket 1 equals to 0 1 column vector, right? So because in this particular point the x component is 1 unit and y component is 0 unit, in this particular point, the x is 0 unit and y has 1 unit, right? So now any arbitrary vector I, which is a superposition of alpha 0, like superposition of this 0 and 1, but I do not know exactly what is alpha and what is beta, right? This is any arbitrary superposition state, right? I don't know what is alpha and beta. Now I have to compute alpha and beta, right? For that, what we do? We do measurement. And one of the measurement is that if you do the projection, right? Because this 0 and 1 are the basis vector. If you do the projection of this psi on the 0 basis, so what you get? Alpha 0 plus beta 1, right? So this particular psi times this 0 state, right? So what I get? Alpha times 0 0 outer product, inner product, plus beta times 1 0 1 0 inner product. Now, if I write this way, so 0 0 inner product is 1. That means I get back alpha, and 1 0 1 0 basically inner product equals to 0. So beta, this particular component will be 0. So I'll be getting alpha back. So if I do the projection on this particular axis, I'll be getting the alpha component. If I do the projection on this particular axis, I'll be getting the beta component, right? Now this is any two particular orthonormal basis, but formally I can have eigenbasis where I can project this quantum state on the eigenbasis, um, and I should get back the quantity, right? So similarly, if I do psi over say 1, I'll be getting the beta component because I represented the quantum information in terms of the basis 0 and 1. If I could represent the quantum information in terms of the eigenbasis, I could directly measure it on the eigenbasis and get back the value. Now, I say I am using the basis as 0 and 1, right? For example, 0 and 1, and these are often called the computational basis, right? Computational basis, which are easy to understand in simple coordinate system, but they are in eigenvalues of G operator, Pauli G operator. So I repeatedly covered these topics in previous QTs, but just those who are new for them, I'm just covering it again. So Pauli G operator is defined as 1, 0, 0 minus 1 matrix, Pauli G matrix, sigma G matrix, sometimes written as, or sometimes it is also written as G operator, right? So if you multiply G with K0, so that means 1, 0, 0 minus 1, this matrix times the vector 1, 0, you'll be getting it as a K0. So that means, and the second, if you do K1, you'll be getting 1, 0, 0 minus 1 times 0, 1. That will be minus of minus 1. So what you get, K0 equals to K0, G times K0 is K0, and G times K1 equals to minus K1. So that means equals to lambda times K0 and lambda times K1, right? So the first lambda equals to your 1, second lambda equals to minus 1. So 0 and 1, that means they are the K0 and K1, they are the eigenvectors of Pauli G operator with eigenvalues 1 and minus 1, right? So how many times you get the plus 1, that gives you the probability of getting the K0 state. How many times out of n quantum experiment you get minus 1, that gives you the probability of K1. So that is what the basically notion of measurement, right? From postulate 3 here, right? So that is simply written as this wave function times the particular basis, and the basis can be a eigenbasis in general, right? Then whatever quantity you get, that quantity squares give the probability. Because if you do not take the square, so it can be any complex quantity, complex scalar number. Taking the square basically gives you the probability that is coming from the postulate 1, right? In terms of the density matrix, because now you represented your psi in terms of the density matrix rho, so then probability of particular eigenbasis an will be traced over Pn time rho. Okay. Now what is this Pn? Pn is the projector. Basically now earlier I was doing in terms of the basically this kind of direct projection. So I can write this also in this. So there is no space. This is often write in this way. This is a projector called P1 projector. One outer product is called the P2 projector, right? So if you simply multiply P1 with the density matrix rho, you will be getting the probability in that particular basis. Similarly, P2 with the rho state psi, you will be getting the probability of that quantum state in K1 state. So in this way, and of course you need to take the trace. And to normalize the post measurement state, so we just need to divide with the norm, and you will be getting the normalized value. The fourth postulate is the time evolution postulate, that is important in terms of the time evolution thing. I'll just I'm posing here because this thing I'll be coming tomorrow. There will be a details on this. So I'm skipping this part for now just to save certain like time thing. So like if you okay, just let me give a very smaller description, shorter description. And let us look at this particular equation, the Schrodinger equation for isolated quantum system. I h bar del del t of psi equals to h hat psi, right? So if you see the left hand side of the particular equation, this is a in fact, I should write del t. It should not be ddt. This is written wrong. So this is a partial differential equation of the wave function. Because why I wrote this as a direct differential instead of partial, because I omitted the space component. But suppose in general, let's take the partial differential form for EG. So this is my Hamiltonian operator on the wave functions, right? H hat psi. And typically this is the Schrodinger equation. Now, if I solve this partial differential equation, PD equation with respect to time, considering the space and time are independent variable, so you'll be getting a solution like this. That solution of the PD equation is that the time evolved state psi t is some unitary operator times the initial state psi t0, where this particular u is defined at e to the power minus I h t. Okay, so this is known as the time propagator. Okay, so now this Hamiltonian can be function of time. It may not be h can be function of time, and h may not be function of time. Okay, maybe or may not be, right? And based on that, actually there are two particular cases. One is called the time dependent Schrodinger equation TDSE, and time independent Schrodinger equation ITDSE. Okay, so now if you have two different time instants, say t and t0 instead of 0 time, so you have this particular operator e to the power h hat t minus t0 is the time gap. And Planck constant typically in computation, because it's a constant, often we take it is equals to 1. It has a value like 6.626 and 10 to the power minus 34 joule second. But in general, in computation for easy things, so we often omit this particular term, and we simply write this time propagator as u equals to e to the power minus I ht, and t0 suppose equals to 0. So this equation is simplified as u equals to e to the power minus I ht is called a time propagator. Okay. Similarly, so in the state vector form, uh, okay, the wave function form is very easy, because the Hamiltonian in physics is written as in terms of simply kinetic energy component plus the potential energy component. But the kinetic energy and potential energy is written as an operator, not quantity. Okay, and that operator is acting on the wave function psi r comma t, which are expected to give the if you solve the equations, they are expected to give the solutions for the kinetic energy and the potential energy. So we can simply divide this equation into two terms, kinetic energy and potential energy, separate and solve it. Or we can do the Fourier transform on the first part. Suppose because kinetic energy is a function of momentum, you can convert it to space, and potential energy already is function of space. So then they are compatible and you can solve it. And density matrix approach, here instead of the Schrodinger equation, we have something called the von Neumann equation, where the state evolution, earlier my state evolution was IH del t psi t, right? On state vector psi, ket psi, right? Now instead of that, I do IH bar del d rho dt. Suppose I take the direct derivative ddt, I omit the space. Then otherwise, if space is there, I can take the partial derivative I h bar del rho and del t equals to commutation h the Hamiltonian and the density matrix, which can be written as h rho. So commutation operations I'll be detailed. So minus rho h. Okay. This should be plus, I think. Okay. So anti-commutation, it will be minus most likely, and the commutation will be plus. So in this particular case, and of course the psi part So this particular quantity will size basically written in terms of the density matrix rho. And once you have this kind of von Neumann form, then in forget quantum state is rho t0, then it will be simply the rho evolved will be u rho 0 u dagger. Okay, so this is the form. Okay, so this is like state evolution. So with starting e to the power minus I h t psi 0, and with density matrix formalism, rho t will be u rho 0 u star. Okay, so where this is equals to u. Okay, u equals to e to the power I h t. And composite quantum system is the coming in the postulate 5. Um, composite quantum system is that the principle is that if you have two quantum system, so this is one quantum system, this is another quantum system, this is qubit 1, then this is qubit 2. And if I want to represent these two systems together, I can better represent them as a tensor product of this particular state. So their joint state of system A and system B will be A tensor product with B. So in mathematics, this is known as the Kronecker matrix product. Now there is an important property that suppose you have individual quantum state Q1 and Q2, right? And Q1 had state say alpha ket 0 plus beta ket 1, and suppose Q2 particular quantum state is gamma ket 0 plus delta ket 1. This is the individual state. Then you can write the component of this particular Q1 and Q2. Suppose ket Q1 and tensor product with ket Q2. This is the composite quantum state. And you write in 4 mathematical bases it can create together, like 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. These are the 4 like mathematical basis in tensor product, because 2 cross 2 system will be 4 cross 1. Sorry, 2 cross 1 quantum system, 2 cross 1 quantum system will be 4 cross 1 column vector, right? So now in this particular state, I have 4 orthonormal bases. And my component, like for example, if you multiply this particular 2 component, it will be alpha gamma 0, 1. So 0 and 1 will be alpha delta. Then this will be beta times gamma, and this will be beta times delta, for example, right? So we have 4 terms. So this way of writing things we often call product state. How we can create a bigger quantum system using small qubit. So using the composite formulations, this is known as the product state. And in quantum chemistry, people often use something called a MPS formulation, matrix product state, where they basically write a very big Hamiltonian of a molecule as a product of smaller Hamiltonian, right, in the MPS formulation. Now there is a very important property in quantum that is called an entanglement. I'll come to define entanglement later. For now, in terms of composite quantum system, is that suppose I have two quantum systems C and D, right? And I have a composite system of C and D, suppose, okay? Now, this is such a state that I cannot decompose in this product. Now, earlier I was saying if I have individual small quantum system, I can write in a bigger way using the using the tensor product, that is called the MPS thing, that is matrix product states. But there might be a composite state in quantum. This is an important feature in quantum mechanics, that even if it is in a composite state, but I cannot break it into the product state. Those kind of states are known as the entangled state. So there are examples, for example, the Bell state, this particular state. So here you can see that the probability, how to create Bell state, I'll come later in the second part. For now, the Bell state I can write in as a 1 by square root 2 0 0 plus 1 1 state, and you can clearly see there is no 0 1 and 1 0 state. So I cannot get the probability, this alpha delta term and the beta gamma term out of this state, right? If I just map this particular state with this particular product state, I do not have equivalent quantity beta delta and alpha delta, right? So these two, beta gamma and alpha delta, these two terms are not there. Only I have the alpha gamma term and beta delta terms, which are super correlated, highly correlated terms. That means if I measure this qubit, first qubit 0, I have all information about the second qubit to be 0, right? Entire probability information. So this particular highly correlated state is known as the entangled state, which is a special type of composite system which don't have any equivalent matrix product states. Okay. So this is coming from the postulate number pi. Any confusion till now? I can pause here and then I'll slowly go towards the solid state part. So just if there is any question, I can stop here. No, right?
If there are any questions, please write in the chat box.
Yeah, please, you can write here. So I'll give a break of 5 minutes and then I'll come back and continue the next 1.5 hour.
Yes,
Is
sir.
that fine, right, ma'am?
Yes, sir.
So, shall I start, ma'am?
Yes, sir.
Oh, yeah. Thank you. Um, so far, we just described the quantum postulates from various angles, from functional description, vector, state vector description, as well as the bit on the density matrix description. Density matrix description will come back tomorrow with more detail from the information theoretic perspective. Just for today, because it's a review of quantum mechanics and the computation part, so I just touched it. So in general, the two most important thing that we just need to remember in the quantum computations, both for the hardware design as well for the computation purpose. So one is the quantum superpositions theorem, that if you have any two valid quantum states, psi1 and psi2, then C1 psi1 and plus C2 psi2 also another valid quantum state. This is a super powerful. This is not only a superpositions theorem, but it's a very powerful theorem in quantum physics and quantum computation. This helps us to design a lot of possible things, and also something it gives called the parallelism, quantum parallelism basically. Okay. So later you will see, if you have say Q1, Q2, Q0, there are three qubits together, right? So it can create a superposition state of 2 to the power 3 particular possibilities. That means individually they can have Ket0 and Ket1 state, but when you represent in the quantum circuit mechanism, or as part of the quantum circuit, superpositions theorem helps them to represent in the state from 0, 0, 0 to 1, 1, 1 state, and which are basically 8 possible states out of only 3 qubits. So that gives basically n number of qubits to 2 to the power n possible states. And that states, if you define, initially create all the qubits from the 0 state, for example, then you can create a computational basis states, 2 to the power n number of computational basis sets possible by controlling on the qubits. Okay, how to control and those things I'll come from the solid state part now. So this is a super powerful theorem, as well as the because you have multiple quantum system. That means the operations we need to understand throughout very clearly is the tensor product formulations. So if you design a quantum state here, if you design a quantum state here, but in general it is representing this entire tensor product of this and this particular wiring together, right? If it is A, if it is B, and there is nothing, that means there is an identity matrix, and the entire state is A times B times the tensor product times the identity matrix. So this is the composite state. Individually, it can be any rotation gets 2 cross 2. It is can be any rotation gets 2 cross 2, but it has a 8 cross 8 dimension after the tensor product, right? Sometimes you'll be getting that control qubit gate, like the C naught, for example. I'll come back and define these gates and all. Then C naught is basically a special type of composite gate which you cannot decompose into the matrix product state like the individual rotation gates, and that's why it is often called an entangled gate. Okay, so these are two important part. And then okay, earlier I wrote this wrong, so this will be equals to h hat rho hat minus rho hat h hat. Okay, so this is known as the commutation thing, commutation operator. So there are two particular operator. One is called the commutation operator. One is anti-commutation operator. For commutation is written as a hat b hat minus b hat a hat. Anti-commutation is written as a hat b hat plus b hat a hat. And we say that two particular operator A and B commute each other if A hat B hat equals to B hat A hat. If this is satisfied, then we say they are commutator or commutating operator. Commutating operator. So then, of course, the commutation between A and B will be equals to 0, right? Because they are equal, that means 0, right? So matrix, often when you do scalar multiplications, you often see that they commute each other. But when you do matrix multiplication, they in general they do not commute each other, right? They can be very different. So from there, actually, something is important that is called the uncertainty in operator, and related to the uncertainty principle as well. So if you have two particular operators, say A and B, they have certain particularly uncertainty in A is delta A and uncertainty is B in delta B, which is greater equals to half of the inner product of the commutation of A and B, right? So this is the uncertainty principle in quantum mechanics. So now we'll show the Heisenberg uncertainty from here. So what is so suppose A is an operator, right? So then the variance of A operator, we can define the variance as the square of the operator A square minus expectation of A hat square minus the A hat expectation square, right? Like the mean minus, so how you calculate the variance, right, of if suppose A has certain probabilistic, right, or a random matrix, for example, right? So because there is nothing certain in the wave function descriptions, right, it has a probability notion. So correspondingly in the operator also it can have a probabilistic notion, and from there the uncertainty in the operator is defined by delta A, and you can define both the expectation as well as the variance. So variance is the like how much uncertainty is there, that is a resolution of the uncertainty in terms of the statistical measure, so which is defined in for A variance of A operator and variance of B operator. So the now if this is the definition of commutator, like the commutation operations between A and B. Now let's take an example. Suppose position is an operator. So if I apply the position operator on the wave function, I get back the position eigenvalue, like x hat psi x equals to x psi x. X is the position eigenvalue or the measurable quantity, where x hat is the operator representation of the space. Similarly, p hat is the operator form of the momentum. If I apply the p hat on psi x, I get the h bar k, that is the quantity, measurable quantity, that is the measurable quantity of momentum eigenvalue basically, and psi x. So now if I apply this, now if I apply the commutation operator x hat comma p hat on the psi x. So first I will apply so it will be x hat p hat p hat psi x minus the p hat x hat psi x. So if x and p are commutable each other, that means they commute each other, then this quantity should be 0. But let's check it. If I basically first you stop this and I just apply the momentum operator and psi x. So this will give you the quantity h bar k, right? X hat on this particular thing, right? So and secondly, if you stop this p hat and simply apply this x hat on the psi x, we'll be getting back the x. So p hat of x, right? So then and of course there is psi x particular quantity, right? So then if you do basically x hat, if you do the operation, so h bar k is the constant quantity, it will go outside, and simply you are applying x hat on psi x. Similarly, x is the constant quantity for this p hat, so x will be coming outside and p hat will be applied on psi x. So what are the quantities we get? H bar x k and psi x psi x. So it should be x hat psi x minus of I h bar psi x minus this quantity. So ultimately it will be I h bar psi x. So you can simply just calculate this. So it will come as I h bar psi x after basically deducting all everything. So this is not coming as 0. So that means position and momentum are not do not commute each other, right? So if they do not commute each other, that means we say there is an uncertainty in position and momentum, right? Then the uncertainty in position and momentum in the desired quantity, right? So that is basically the x hat and p hat equals to I h bar this particular quantity, we say this is the Schrodinger, this is the Heisenberg uncertainty in position in space. Similarly, you can compute, for example, energy operator or the Hamiltonian operator and the time operator. So you will be getting certain, basically the commutation of this is also not equals to 0. So that means there is uncertainty in time and energy. There is uncertainty in position and the space, right? So this is the uncertainty principle in basically quantum physics. So this is also important when you design certain algorithm. For example, you are designing a quantum algorithm to compute certain spectral density or spectral component, for example. So maybe ground state, right? So if you want to compute the ground state of a particular molecule, right? What is the basically uncertainty in positions and uncertainty in energy, and those things you can compute from this kind of principles. So density matrix, okay, I'll come back this part tomorrow because I'll come back in the information theoretic stuff, and this is important there. I'll just keeping this part here. So although I gave a brief description earlier, but I'll go in detail tomorrow. Okay. Now there is something important. So one is the Schrodinger picture, one is the Heisenberg picture, and one is the interaction picture that basically interact both the pictures, Schrodinger and the Heisenberg picture. In short, what we have a state psi, right? Say it is at time 0, and we have an operator u of t at t0, right? And after t0 to t1, or some say t equals to t, some particular future time, I have a future state, say psi t, and I have a future um, operator at say it is at t equals to t0 and at t equals to t, right? Or t1. So simply say t equals to t1. Okay. Now these two picture tells two different things. So first is the Schrodinger picture. What it tells is that when you evolve from a particular state, suppose you describe our entire quantum computing, mostly circuit phenomena. If I represent a quantum state as psi t, right? I apply mathematical operator and I get psi t1. Say psi t0 to psi t1 is another vector. Okay. And in this particular process, the mathematical operator I apply here, I say this is mathematically invariant, right? The component of this matrix are mathematically invariant, right? And then basically the entire time notion is embedded within the state vector only, where time evolution operator, the time propagator does not change with time in a sense. That means the component of this time operator are not a function of time. They are fixed with time. The state evolve over time given a static ut. Okay. So that is the picture covered by Schrodinger, where state evolves, not the operator, right? So this is here you can see the equation. So you are basically evolving over time. That's why derivative over time on that particular state, not on the operator, right? So this particular picture is known as the Schrodinger picture in the density matrix form. Okay, rho S, this particular S represent the Schrodinger. Okay, and later we'll see H for Heisenberg. These two particular notation. So here, if you have an initial state psi 0, psi t0, and future is state is psi t. So psi t is basically time propagated times the psi t0, right? Here the propagator is fixed, right? Only your state is evolving. The Heisenberg picture is opposite. Here, what it says is that your state does not evolve, your operator evolves. Okay, so that's why we write the basically the time evolution equation in terms of the operator, not in terms of the state. So suppose your operator is a. So now you write the derivative of the operator. That means time evolve of the operator is represented as I h bar h time operator. So I'm not writing any state vector. I'm writing the operator form plus something extra part. right? Delta AH had delta T explicit. Okay. So this is often written as the equation of motion for operators by the Heisenberg picture. So here you fix the state, that state does not evolve, but the operator evolves. So once the operator evolves, so there is a way, like there is a total derivation of the steps and all. I'll be sharing the notes. I'm just not following all the details. So of course, here actually your observable, you can see it is evolving, right?
Sir, your screen is not visible. Sir, your screen and voice is not audible also.
Hello, am I audible?
Yes, sir, you are audible, but the screen is not visible.
Just it is disconnected due to network issue. Just 1 minute. Actually, my Wi-Fi has gone. Like I'm connected from my mobile. I'm so sorry. I'm trying to get connected.
Sorry.
the weather is too bad today. It's lightning and raining a lot outside. Um,
Sir.
is it visible now, ma'am?
Yes, sir, it is visible.
Yeah. So I'm just let me connect only from one device. That will be easy. Yeah. Thank you. Mm, yeah. Okay. So we were discussing about the both the pictures, the Schrodinger picture versus the Heisenberg picture. In the Schrodinger picture, state evolves where the operator is kept intact, and in the Heisenberg picture, where operator evolves with the commutation form. This is known as the Heisenberg form or Heisenberg equations of operator evolution. Keeping that state is not evolved over time. And there is an interaction picture, so not going to the details of that because of time, so I'll be sharing the notes. So where um, um, you two part H0, and you have a perturbability part, that is the V hat T part. So the H0 part is known as the free part, and whereas the perturbability part is Vt. And you do the evolutions, one for the H0 T part, another part for V hat part. And by this way, you write the equations to relate basically the operator form with the state evolution form, where state you write as the interaction state or the evolved state is the initial state with the perturbative evolution. So this is the basically time dependent perturbation theory starts from here. And basically you write the evolved state in the Dyson series in this form. Often we often call this is a Dirac formulations of the quantum mechanics, right? So in general, in short, is that in one picture that we write the state evolution form, right? How our state evolved over time. That is the simple thing we do in quantum computation. In some of the error mitigation techniques, tomorrow probably I won't be able to capture the details, but I will just touch the things. The Heisenberg picture is also seen in some of the cases. For example, the some of the operator back propagations phenomena, basically circuit depth minimizations, etc. We'll also consider that we'll keep fixed of the quantum state, and we'll design certain equivalent quantum circuit with the reduced depth, and then basically we apply the quantum state to evolve over the reduced depth. So both the Schrodinger picture and the Heisenberg picture will be equivalently used in some of the circuit phenomena. Okay. So spectral decomposition theorem, I just already explained. I'm just skipping this part. Okay. In quantum gates, actually, there are some of the basically important gates, and Pauli gates are like sometimes they are the important rotation gates along x-axis, y-axis, and z-axis rotation. So this is the Pauli X written as this. This is also known as the NOT operations or NOT gate in quantum computing. 0, 1, 1, 0. This is the sigma y for the y rotation. So 0 minus I 0, and sigma g operator, typically often used in the measurement and many other cases. So 1, 0 and 0 minus 1 particular thing. Important relationship is that the square of the Pauli matrices equals to the identity matrix. That means if you multiply the sigma x times the sigma x, or the sigma x star times the sigma x, you'll be getting the identity matrix, and same for all others. And if you do this cross multiplication, this is the relationship. So in general, any rotation gate you can represent in this cos theta by 2 identity minus I sin theta by 2 n hat sigma, where sigma can be sigma x, y, and g. Now, okay, so quantum measurement, I discussed the projective measurement part, and some other parts like POVM and there are certain theorems called the Nymark's dilation theorem. If you have a non-unitary operator, how still you can represent on a quantum computer using the dilation, using the ancillary qubit. So there is certain theorem called the Nymark's dilation theorem. So I'll be sharing the documents for this, those who are interested. These are bit advanced topics, so some of the reference materials will be given here. So in general, we'll be using the projective measurement, and in some cases the POVM are important. But in general, mostly the projective measurement will be done. So I have shown, like, if you have a qubit, so how you basically project it into the 0 basis and the 1 basis in multiple eigenbasis, and you get the desired quantity. This is the same thing. There is also for the noisy quantum system, there is a quantum channel description, the complete positive trace preserving map, CPT map, and often they are represented by Krauss operator K. So there are various kind of channel that if there is an environment, there is a quantum system that is interacting with the environment, because there is no isolated system. Every quantum system does certain interactions with the environment with certain level, and you can model that using various mapping technique like the amplitude damping, phase damping, depolarizations using the Krauss operator map. So tomorrow I'll discuss more on this CPTP map and all. Okay, now next, I think I covered the basics quantum mechanics things, and I'll now talk about some of the solid state part and the quantum computation formalism. So often when we talk about logic, right, um, we say that our computation formalism understand the 0 and 1 bit string, the classical bits 0 and 1, and how we create those classical bits. So there are logic, right? In semiconductor physics or semiconductor technology, we know that there are various kind of logic, transistor logic, TTL logic, right? And then basically there is CMOS logic, right? And the large scale CMOS based VLSI technology, where you have a silicon wafer and you do doping, right? Say in some places you do N-type doping, in some places you do P-type doping, and you create certain channel, right? And within the channel, basically carrier flows. Carrier can be electron, carrier can be holes, right? Say for example, if you create this kind of basically MOSFET, where you have to N plus region, that means dominated by the negative charges, right? The electrons, right? And P-type substrate means the holes majority is the, okay, there is a question. Okay, let me take the question. Um, what are the applications of Schrodinger picture, interaction picture, and Heisenberg picture? So Schrodinger picture is the standard one. Like you do everything. Like you represent your data in a quantum state vector, and then what you want on the data, you want to do certain mathematical transformation, either Fourier transform or certain basis transformations, in order to better understand your data, in order to classify your data, in order to predict the future inference from the data, like whatever operations you want to do on the data itself. So that means you do evolution of your quantum state. That's the directly the Schrodinger picture. And all the quantum gate operations you do, like the Pauli X gate, Y gate, G gate, rotation gate, C naught gate, nowhere you consider that those gates evolve over time. They do not change, right? So that means this is the Schrodinger picture. Heisenberg picture sometimes used in quantum computation formalism for various error mitigations and circuit depth minimization techniques. Those are also important. But the use cases are very, very less. Yeah. Interaction picture, I actually don't know what are the use cases in quantum. Of interaction picture in like a study of magnetic materials, quantum material, quantum sensing, and many places, not directly to quantum computing. I mean, there might be, I don't know. Yeah, I'll be taking all the questions last 15 minutes. So, um, so we control the flow of electron by using the gate voltage, right? Gate to source voltage and gate to drain voltage, these kind of operations, right? How you basically control the width of the particular channel and the flow of the electrons, right? And that gives you the amount of current and voltage, right? So based on that, we have certain types of material called the PMOS, where dominated by holes, and the NMOS dominated by the channel is dominated by the electron. So if you have this kind of PMOS NMOS configuration setup, often we call the inverter circuit, right? And in this particular configuration, so if you give the V input voltage to be very high in this particular case, so if you give the this particular voltage very high, this basically channel is the gate voltage applies to be very high, then there is the channel width is very low and the current is hardly passed. But in this particular case, channel is widen and basically easily you get the ground voltage here to be zero. So that means you give a high voltage, you get the output to be low. And similarly, if you give the voltage to be low, this particular channel, PMOS channel, will be flattened and the current will flow from the source plus 5 volt towards the V output. And this particular channel will be actually narrowed down, right? So this is the basic fundamental of the inverter circuit, right? And equivalently, what we understand that there is a voltage up and voltage down. This is the scenario. And in the compiler, you define that this notion of high voltage and no voltage with the machine level language to be 1 and to be 0, right? And that you define in the quantum computer. That's what is actually the bits 0 and 1, how we define in a classical computer. Now, in a quantum computer, so you have seen the chandelier, right? So in the bottom of this entire quantum cryogenic setup, this small unit, within that, this is basically a magnetic shield, and within the magnetic shield, actually, even this is placed in a very millikelvin temperature, very low temperature, right? And within that, to minimize any magnetic interference or any kind of interference, there are so many shields, and within that, there is the quantum chipset. And within the quantum chipset, actually, there are qubits are designed, right? So for example, let me give you the example of superconducting qubit, although the other qubit technology has the different architecture. For example, topological phase qubit, spin qubit, like trapped ion qubit, the NV diamond center. So all they have the different way of describing things. Superconducting is a very like one of the like most interesting and well researched topic. Both IBM, Google, and some other companies are developing quantum computers on this particular technology, superconducting qubit technology. So I'll be talking bit on this for 5 to 10 minutes, and then I'll go towards the computing part. So this particular chip has 5 qubit in this example, and each particular qubit are actually made up of artificial atoms, and that artificial atoms has multiple energy level. So how do we create this kind of atoms? I'll go bit detail just in the next slide. So these are typically Josephson junctions um, uh, based artificial atoms of the circuitry. Often we call the transmon qubit, and this creates this kind of LC oscillator type of circuitry, where you have the L part, that is the magnetic flux part, as well as the capacitance part, and you can control the frequency of this circuit by omega equals to 1 by square root LC, that particular formulations. And you can create certain energy level of this particular configurations, like the ground state, the first excited state, or multiple energy state. In a 2 information level computation, often we call qubit, like the information lies between the ground state and the first excited state, gate 0 and gate 1. So these are the energy levels, and you discard the upper higher energy level for computational purpose. So mathematically, these are equivalently written in the basically computational basis object. In circuitry, these are various important frequency components within which you vary the voltage and current in a controlled manner. In molecular level or the artificial atom realizations, these are energy values or energy states in an artificial atom. Okay. So typically, if you see the temperature versus the state of a particular system, right? For normal metal, this is the plot, and for superconductors, actually, if you consider the superconductor material, so they have a particular temperature called Tc. critical temperature, okay, where actually there is a basically fall, right, of this particular curve you can see. So for details, I have referred this particular archive research paper that you can just take a photo of this, and you can read the details of how this superconducting material works. So various materials have their different critical temperature, right? For example, aluminum has a critical temperature of 1.2 Kelvin, right? It is used widely used for the qubits and resonator. So what is a resonator? So you all know, right? The LC oscillator resonator, how to prepare and all in the electrical thing. Niobium is another widely used material which has critical temperature of 9.3. So these are the list of various for example, the niobium nitride, niobium titanium. So they have not only the critical temperature, there are other things like how you can efficiently control them, what is the availability, what is the price, what is the environmental impact. There are a lot of things, engineering challenges are there to pick up a particular material suitable for the qubit design, right? Now, okay, so I'm not going detail. So in order to design the qubit, there are certain technological revolutions. So you can study. I'm just keeping, just giving an overview of the things. And if you are interested, you can just go and study. One is the Cooper's pairs and macroscopic quantum coherence, right? So basically, there is a concept called the phonon, right? So when basically the one is the photon and one is phonon, right? So this phonon is another kind of quantum phenomena when basically there is a transition of energy within um, the the uh, the fermionic, if you consider, for example, the electrons, right? So within the orbital level, they change, right? So phonon phenomena is relevant there. So below the critical temperature, phonon mediated attractive interactions pair conductance electrons into the Cooper pairs. In the bosonic bounds, basically these charges can be minus twice of the electronic charge. Spin can be zero. So there is a description of that. And the broader things are discussed in the BCS theory, like the Bard-Cooper Seyfert theorem. So how the superfluidity current works and all, how you create a certain quantum state using the Cooper pairs and all. There are certain primitive theories. The modern theories basically designed on like the initial earlier realizations of the qubits were mainly based on the Cooper pair box Hamiltonian, how basically you can control the phonons and all. So there are certain physical configurations how you create a particular quantum state using the charge induced basis sets and all. Later, actually, people have tried to control more on the frequency of the oscillator type of circuits using the Josephson junctions, or the Josephson effect of the Josephson junctions kind of thing, where there are a particular way how to create the Josephson junction. For example, the semiconductor versus insulator, semiconductor versus semiconductor, semiconductor constriction semiconductor. So there is various ways how you actually create this kind of effect. And typically you control two kind of effect, DC effect and the AC effect, and utilization of that as a whole to create the magnetic flux as a core component of the qubit operations, right? So the technology evolved, and people come up with the idea of circuit quantum electrodynamics, CQED. This is another technology. I think these are well taught in this subject. I'm not going detail to these things. So there is something called the Jens Cummins Hamiltonian, and how to use that to create the dispersive the QND, and together with that, how to create a particular measurement quantity, readout quantity, right? Like the QND measurement, etc. So, and what are the typical frequencies we should choose and all. So these are some of the physical constraint and design in the superconducting qubit. So when I say LC oscillator, so immediately something comes to our mind is this particular circuit we typically see, right? And this is a resonator circuit. If the design matches with the component value chosen to define the resonator properly, LC circuit to be a resonator. So there are certain equations to derive from the coming from all the magnetic flux equations to all this defined. So I'm not going detail to that. Now, instead of this L part, now you put this Josephson junctions part to have more control on the induction part, the flux, magnetic flux part, and you have a supercapacitor here, right? CS part. So these two components together help us to create scale and gate one. You can have more component in general. So there are engineering to basically eliminate those energy level in the computation part. So the gap between this gate one and gate two state, or the higher energy state to the first excited state, to be should be higher than the and the energy gap between the ground state and the first excited state. So there are certain challenges on that. So those who design the qubits, they take care of all these details. And then basically now once you design the qubit, right, and you represent this quantum registers to basically encode your data in the quantum registers in terms of these in terms of this superpositions, entanglement, interference phenomena. So you need to create the control operations on the qubit, right, in order to do certain operations on the information. For that, what we do, suppose for example, you want to do rotation of a quantum informations, right? So rotation gate or the entangle gate. So there are physically we need to do the microwave pulse operations. So on the superconducting series of circuit, you do the microwave pulse operation. So there are certain techniques, for example, pulse shaping, various envelope design, suppressions leakage like drag technique. So these are various techniques how you do various gate control operations on the quantum state. So gate operations means you are basically doing the time evolutions things, right? The quantum simulation stuff, or what you are operating on the wave function. So initially I was saying the observable thing and all, right? Or operator, applying the operator and getting the observable or the measurable quantity, right? So this is the gate operations are related with the microwave pulse control on the superconducting qubit or the transpond qubit. So in general, the picture is something like this. So you have a room temperature, you have a local computer, and you have a cryogenic chamber. Within the cryogenic chamber, you have the quantum chipset or the QPU, quantum processing unit. So those um, so so in general, so what happens is like this. So suppose you have now. So you have one is the LC type circuit like this. Suppose this is your L and this is your C, and there is a control voltage. And suppose there is another level of control, and suppose this particular part is your Josephson junction. So this will be, and this is the supercapacitor part, CS part. So this particular part is the resonator part, and this part is the transpond qubit part, where you have a dedicated basically the Josephson junction based particular magnetic flux controlled way. And this particular part is the suppose a superconductor CS. Okay, so you have a coupled system like this. So this is a resonator, qubit resonator coupled system in this particular case. And this part is kept within the millikelvin temperature, whereas you have control electronics like amplifier, demodulator, modulator, etc., and various analog components, for example, the signal mixture, right? Various local oscillator, etc. So what you do is that you create a quantum information out of this qubit or the qubit resonator coupled system. Then you want to operate on this qubit. For example, you have a gate state gate 0, and you apply, suppose this quantum state gate 0 to, you want to go to gate 1. So this write up would be quite bad handwriting, because now I am disconnected from the iPad. So I'm just drawing, we using mouse. So now you apply a quantum gate here. Suppose you apply the Pauli X gate. So if you apply the Pauli X gate, and your information becomes from gate 0 to gate 1, right? This is the very simple gate operations, because this Pauli gate is basically your Pauli X is 0, 1 and 1 0 matrix. So if you multiply this 0 1 1 0 matrix with gate 0, you'll be getting gate 1 and the vice versa. Now these gate operations, to do this, I have to do certain microwave pulse control thing and apply from the outer world to this cryogenic world, right? And whatever result I get, I basically whatever state I get, I do certain readout measurement, and then I amplify the voltage or current informations to the again to the room temperature. So this is the control qubit control setup, actually how it works in the physical hardware. Okay, and you get the information back. Now when you get from this low temperature to high temperature and high temperature to low temperature, you can understand the how challenging it is in the quantum computer, because whether this qubit within that particular time, whether this qubit actually will lose the coherence, whether these informations can be noisy or not. So there are lots of corrections are needed, right? The separations are needed, mitigations are needed. That's why this error mitigation stuff, error correction stuffs are important as engineering technique. Now instead of going to the more details on this, like how the transmos resonator bus works, like the circuit I was drawing, this LC and this resonator and all for various couplings, like there are GG coupling, G coupling, and there are different way of doing the coupling. So if you are interested, you can go through this particular material for more details. Now there are different kinds of basically gates. So those who actually work on real quantum computer, you can see that the quantum gates we look at in the textbooks in general, for example, the Pauli operators, Hadamard, the various T gate and other gates, they may not be always available in the physical hardware, because physical hardware actually that does the actual operations. They have a particular native gate set, right? And those native entire quantum computing algorithm should be um, design or redesign into that particular basis gates that is available native to the hardware. Some of the things are like cross resonance gate or the ECR gate, echoed cross resonance gate. So they have the definitions like this. Swap gate. Swap gates already we know from reversible quantum computing logic, right? ISWAP gate is an interesting gate, and this square root ISWAP gate is often is used in the Google's Sycamore quantum computers. In IBM ECR, CNOT, CZ, these kind of gates are quite popular, right? So this has also related notion in the hardware. What kind of equipment I should be using, what kind of microwave pulses I should be choosing to, so that I can do this kind of mathematical operations, right? Um, this is an important decomposition known as CAC decomposition, CAC decomposition, or 2-qubit basis decomposer. This might not be taught previously. I think nobody has covered this one. So this is even not that popular also. In general, if we have a big algorithm, right, a big operator, suppose you want to do, say, certain mathematical transformation on a particular data set, right? So suppose you have some data set X, and you have a mathematical transformation, say mathematical transformation A, and you have an outcome, say Y. So Y can be this can be a classification problem, this can be a clustering problem, it can be a prediction problem, it can be a simple operation research problem, where your outcome observable or labeled information is a matrix times an input informations, right? Similarly, in quantum, if you have this encoded, input X has an encoded state, say ket X, then and you have a label or output state, say ket Y, right? And equivalently, you should have a operator which is unitary operator, because the time evolution should be unitary in nature. It should be a basically unitary operator. For unitary operator, the definition is U star equals to U inverse. Okay. U star equals to U inverse. So that means U star U equals to identity matrix. So now the theorem says that if you have a big such matrix, you can always decompose into the 2-qubit and 1-qubit gates as the tensor product form. And the 2-qubit basis decomposer is also known as the CAC decomposer, where any U that is in SU4 can be written as this is super unitary operator. In some QT, I discussed in detail about the super unitary operator, so I'm not covering this again. So any unitary operator that is in SU4 can be written in CAC form or Will chamber decomposition form as A1 tensor product A2 e to the power I times basically coefficient times the Pauli XX tensor product, coefficient times YY tensor product, and GG tensor product with the coefficients times B1 and B2, where AI and BJ, AJ and BJ, this particular matrices A and B, they are SU2 local. That means this can be 4 cross 4 unitary matrix. So these are two unitary matrix, local unitary matrices, 2 cross 2, 2 cross 2. And so this 4 cross 4 entire matrix you can write in the 2 cross 2 and 2 cross 2 form. And these are basically this coefficient C, I, C, Y, and Cj. These are basically some values to be chosen from 0 to pi by 4. Okay, interactions coordinates. So this is a particular decomposition of a SU4 into SU2. Similarly, you can decompose 1-qubit Euler decomposition. So for example, if you have a GYG basis, so you can write e to the power I omega times RG theta. So the details you can find here, how you can decompose a big operator into 2-qubit operator and 1-qubit operator. So the decompositions are detailed in these references. So in general, if you have a set of uh, if your operator, mathematical operator, is unitary, it should be in general represented in terms of the Pauli operators. Okay, Pauli, I mean, better to say Clifford and non-Clifford operators. So what is Clifford and non-Clifford? Come. So one is called the Clifford and another set is called the non-Clifford gate. So XYG, Pauli X, Pauli Y, Pauli G, these are Clifford gate. Okay. And there is a pi pulse. So these are the various hardware cost. Okay. So what are the various hardware cost for various gates? This XYG are known as the Pauli gates. So H gate is called the Hadamard gate. So that this looks like this 1 by square root 2 1 1 1 and minus 1. So I'll come to the definition, the mathematical definition I'll come. In general, in previous QTs, I gave the very detailed of the mathematical part only. Now, actually, I'm just trying to capture some of the hardware cost. So this X, Y, G, H, and the S gate, also known as the phase gate, all these are Clifford gate. T gate is known as the non-Clifford gate. So basically, some of the non-Clifford gate actually can be represented in terms of T gate cost. And this is the costly gate, in fact. So these kind of gates, actually the Pauli gates, the phase gate and the Hadamard gate, and also the C0 gate, these are together known as the Clifford gate because they obey the Clifford algebra. So Clifford algebra means the product of in between of this component of the Clifford algebra is also another component that is present in the Clifford algebra. So if you multiply the sum of the components, say x, y, g, h, s, and c naught, you will get the component within this again. So that is the Clifford algebra, but not true for the T gate, right? So that is the non-Clifford part. So together with this Clifford and non-Clifford, is they form the universal quantum gate set, right? Now, if there are certain quantum operators which you can efficiently represent in the Clifford gate set, so this is known as the Gaussman-Neal theorem, that quantum circuit utilizing only a restricted set of operations, that is the Clifford operations, that there is no T operations, that can be perfectly simulated on conventional classical computer in polynomial time, right? But in general, in order to do both the Clifford and non-Clifford operations, so together with this Clifford part and non-Clifford part, which form the universal quantum gate set or universal quantum operations, for that this can be exponential time for the classical computer, and you need a quantum computer for that. Okay, so Gauss-Mann-Neal theorem just only applies for the Clifford group set. Okay, and okay, this is just a comparison of Clifford gate and universal quantum circuits. Okay, CCZ. What is CCZ? Let me tell. Okay, if you have a Pauli, say X gate operation, so typically it looks like this. So you have a circuit and you just apply the X. Okay. Now, if you apply it as an entangled operation, so then you can use the X as a target and basically target the first qubit and controlled by the second qubit. So X you put here. So this is a CX gate. Now, if you have 3 qubit control gate like this, so which is controlled by the first qubit and second qubit and basically applied on the third qubit. So this is a CCX gate. So this is CCX. This is CCX. Similarly, there is something called CCG operator. So control, this will be Pauli G operator. So CCG operator. So this is a universal, a part of the universal gate set. So these are various multi-qubit gate often we use in the circuit design. So this is an important quantum encoding technique. So although I am not today covering encoding technique in details, but just for simplicity, just for giving a notion. So GG feature, how you encode your classical data on a quantum computer, and specifically for example, the quantum machine learning application. So you have a lot of classical features, right? And you want a efficient mapping technique to encode your classical data on a quantum computer. And for that, GG feature map is an important quantum tool where your big quantum circuit, okay, that means the quantum circuit where you design, you encode your information on a quantum machine. So that particular encoding technique can be done, classical data to quantum mapping can be done by some UX, which is a product of C0 matrix, product of C0, product of G, and product of H. So for example, for a 2 qubit circuit, it looks like this: 2 Hadamard gate, 2 rotation gate, 2 C0 gate, and there is in between another rotation gate. So this is R theta 1. This is R theta on, this is also R theta 1, but on data 1. Okay. And so this is the, for your, for example, your classical data first point is x0 and classical data second point is x1. Okay. So two R theta gate, and there is another R theta here. Say this is R theta 3, and these are basically C0 gate. This is, and this is C0 gate. So this particular architecture of this C0 ring, where in between there is a rotation gate and there is another 2 rotation and the Hadamard. So this particular setup is known as the GG feature map. So this GG feature map is an important decomposition like of your circuit, or important way of encoding your classical to quantum data mapping technique. So this is also how we decompose unitary matrix in an efficient way to encode data in a quantum computer. This is just an example I'm giving, not detailing the encoding theorem. So I'm giving a pause of 2 minutes. So if you have any question, please drop in the chat box, and I'll come back to the, now the interesting part will be computing part will come now. So just waiting for 2 minutes. If you have any question, just please drop in the chat box. Okay. So I think there is no question. Now, the okay, is there any question? Let's see. How can we go in depth using IBM? Okay, IBM is a software company. We can help you enable how to use quantum computer with as much possible in terms of the computation part. Theory, I think there are lots of research papers, even from the IBM side. So those might not be present in the Qiskit tutorial or website, but things are there in the publication. So you can search on, you can give a topic name and you can search on the Google Scholar, the IBM papers you can get. Like for example, the how the transmon qubit work in IBM machine or those stuff, right? So those kind of things might be, some details might be there. But due to like IP reason, you may not get every details, but sufficient details might be there for academic reason. Yeah. Yeah, and some of the reference already in my slides are already there, so you can have a look. And for additional resources, I think those things are available in IBM web page, especially the Qiskit website. I'll be sharing those things as well. Individually might not be possible, but some general resources I'll be sharing. Yeah. Okay. So the state representation now. Now, how to represent a quantum state on a blosphere? So that's a three-dimensional represent. That's a spherical representation of quantum informations, which are easy to understand. So, for example, this is a particular configurations, spherical configurations, where there is x-axis, g-axis, and y-axis, and you represent your quantum information kit psi on this particular sphere called the blosphere. So this is named after the scientist. It gives a very good geometrical representation of the quantum state. For example, if you want to represent the quantum state only in Ket0 state, right? That's the computational basis Ket0. So this is the state along the g-axis. Similarly, the beauty of this is and how it is different from the Cartesian coordinate system is that in Cartesian coordinate system earlier I was representing this was my Ket0 and this was my Ket1 from the Cartesian coordinate system, because in Cartesian coordinate system this is my 90-degree angle, right? That gives the orthonormality of these particular vectors, right? In the blosphere representation, suppose this is my g axis, right? So if this is 0, then this is 1. In blosphere, opposite polarity gives the orthonormality condition. So this is the major difference. Okay. So these two opposite polarity points gives the orthonormality in this particular configuration. That's why you can see the Ket0 state is here and Ket1 state is here. Now Ket0 plus Ket1, this is a superposition state with equal probability. It's coming towards the x-axis direction. So here you can see, and the Ket0 plus I into Ket1, this is another superposition state and represented in the y directions component is this particular vector. So these are various ways to represent the quantum information. Now, how to get this particular state with equal probability is to apply the Hadamard gate here on this particular state. Like on Ket0 state, if you apply the Hadamard gate, so you'll be getting this particular state. And if you apply the Hadamard gate on one state, you will be getting minus of this particular Ket0 minus Ket1 state, just opposite. Right. So this is just a representation. Now for a clarity, I have drawn certain picture. So this is, now suppose this is my quantum state Ket psi, and I represent in the Cartesian coordinate system. So this is my Ket1, this is my Ket0. And what operation I can do on a, because it's a 2x1 vector, I can do the rotation operations, right? Suppose I want to go from this point to this particular point, right? So mathematically, I need a rotation matrix cos theta minus I sin theta cos theta. So r pi by 4, for example, if I do the pi by 4 rotation, 45-degree rotation, so this matrix will be 0 minus 1 1 0. Now suppose I want to do quantum, I want a quantum gate that will give me from 0 to 1 state. So I choose a rotation matrix 0 1 1 0, right? And and ket0 is, of course, this particular component of ket0 is I wrote it opposite. Okay, so this is wrong. This is ket1 to ket0 state, and vector notation I have to give. So this is a ket1. So basically, if I apply the rotation gate 0 1 1 0 and multiply with 1 0 vector, so this after multiplication you can see like it the component become 1 0, right? 0 times 0, 1 times 1 is 1, 1 times 0 plus 0 times 1 0, so basically 1 0, and this is basically equals to your gate 0 state. So you can do the opposite as well. So this is the Px gate. So this is typically a rotation gate, we can see, right? And this is on the Qiskit, it is represented like this. Is there a question? Let me see. No. Okay. Similarly, and in Qiskit, when you design the circuit, it's like QC.x. It's simply the quantum circuit. If you represent with the variable QC, you just write QC.x, and which number of qubit you have to give. It is qubit, say first qubit is 0. So it will design a circuit like this. Okay, I'll give a separate notebook for this later on some other time. So, but in simply, you apply the X gate. X gate means this rotation matrix, and it does the basically inversions of the component like 0 to 1 and 1 to 0. Immediately, once you apply the X gate, then your state goes from 0 to 1. Now, I was telling this one, suppose I have a quantum state psi, and it has some component alpha times 0 plus beta times 1s. That means it is in the superposition state. So if you take the projection on this one component, so that is the inner product of 1 and psi, that will give you the component beta. And if you do the projection on this particular basis gate 0, so you'll be getting inner product of psi and 0 will become 1, A. So A is the component in the basis 0. And if you take the square, you will be getting the probability. Now come to the phenomena called superposition, right? So superposition mathematically is that if you have any vector and if you have certain orthonormal basis set, you can represent as a linear combination in that particular orthonormal basis, right? Set of the basis. So for example, if you have two computational bases 0 and 1, you can write A1 0 plus A2 1, where A1 and A2 are two coefficients. If they needs to obey the first postulate of quantum theory, then A1 square plus A2 square equals to 1, just to satisfy the probability law. In general, for superpositions, this conditions is needed. As soon as you import the involve the quantum computation part, this square sum equals to 1 to basically satisfy the probability. Similarly, if you have two eigenbases, say E1 and E2, and two coefficients C1 and C2, then you can represent your state vector as a linear combinations of eigenbases. So any orthonormal basis set, if you have B1, B2, C2, C3 or whatever, so you can represent your vector in that basis set. So that is the mathematical superpositions theorem, right? So in Qiskit, suppose you want to just understand the coin toss experiment, right? So what you do, suppose you have head and tail, right? And you suppose you design basically you start with a qubit Q0, say for example, and you start with the state say 0, and you apply a Hadamard gate. So what does this Hadamard gate, what it does on the gate state 0, it makes it plus state. From the 0 state, it makes it the plus state. So that means the Hadamard gate is 1 by square root 2, 1 1 1 minus 1. Now if you just basically apply this matrix on the 0 state, you will see your effective state will be 1, 1. If you just simply do the matrix vector multiplication, so you'll be seeing your effective state is becoming 1, 1. That means 1, 1 means 1, 1 means this is 1, 0 plus 0, 1, right? There will be a normalized factor, that is 1 by square root 2. That part will be there. So that means this is equals to your normalized part times Ket0 plus Ket1 plus Ket1. So that means I start with Ket0. But if I apply the Hadamard, I'll be getting 0 plus 1, which is written as plus state. So, and if it is minus, this is written as minus state. So plus state means I have the equal probability of 0 and 1. Now, if I repeat this experiment for several times, right, and I measure it on the 0 basis and 1 basis, I'll see that out of 1000 times, nearly 500 times is 0 and nearly 500 times it is 1. So for large number, probabilistically, I'm getting half of the time 0 and half of the time 1, which is a coin toss experiment, right? This simply just by applying the Hadamard gate. Now, a bit deeper circuit, that is the entanglement operation. So now if I apply two Hadamard gate into qubit, right? So eventually I started with 0, 0. So what are the possible states now because of the composite system 0, 0, 0, 1, 1, 0 and 1, 1. And because I applied the Hadamard gate, which has the coefficient 1 by square root 2 and 1 by square root 2. So that 1 by square root 2 times 1 by square root 2 gives you half, and square of half gives you 1 by fourth. That means I have equal probability of all the 4 bases 0, 0, 0, 1, 1, 0 and 1, 1, right? Just by applying two Hadamard, the composite system, right? If I do measure over here. So this is just simply creating the superposition on all 4 bases. But suppose instead of the Hadamard gate here, first qubit I apply Hadamard and second qubit I apply between the second and first qubit I apply a C0 and I omit the second Hadamard from here, right? What happens? So if I look from left to right, so step 0, 1, 2, 3. So along the basically top to bottom, I can see number of qubits, and left to right, I can see the time steps, right? So first step, there is nothing. That means I initialize with 0 and 0 state. So first qubit is 0 state, second qubit is also 0 state, and they form a composite quantum system 0 tensor product with 0. Now once I apply the Hadamard gates, first qubit state becomes plus state, and second qubit state, because the second qubit, like the Q1 qubit, there is nothing, so it remains state 0, right? The plus state I can write it as 0 plus 1, just I saw in the previous example, normalized by square root 2, tensor product with 0. Now if I do tensor product, what it becomes? 1 by square root 2. Now 0 tensor product with 0 and 1 tensor product with 0. So 0, 0 plus 1, 0 by square root 2. Now if I apply a CNOT gate between second qubit and first qubit, that is Q1 and Q0, what happens? The philosophically, to understand this is, when the first qubit is 0, it does nothing to the second qubit. When the first qubit is 1, it flips the second qubit. Okay, it flips the second qubit. Any control gate, if the first qubit is 0, it does nothing to the second qubit. If the first qubit is 1, then it basically does certain mathematical operation on the second qubit. So if I apply the CNOT gate between this first qubit and 0th qubit, 1 and 0, then this 1 by square root 2 will be outside. Then 0 qubit is 0 and second qubit there is nothing, means identity operation. 1 is 1, and because the first qubit is 1, it basically does the X operation, that means flip operation on the second qubit 0. Immediately it becomes 0, 0 plus 1, 1. So I don't have a state which is 0, 1 or 1, 0. I have only 0, 0 and 1, 1 state, right? So this is known as the Bell state. So this particular circuit is called the Bell state circuit. And I cannot break this particular state into the product state of individual qubit. That's why it's basically a particular phenomena that is only possible in the 2-qubit scenario. I cannot break into single 1-qubit operations, and I cannot show in that way. And because I don't have this 0, 1 and 1, 0 state, immediately the probability propagates from this two particular state to 0, 0 and 1, 1 state. And this particular state has 0.5 probability. If you just simply do the measurement on the 0, 0 basis and 1, 1 basis, they are 0.5. If you take the square of square root 2, this will be 0.5. And other component like 0, 1 and 1, 0 that is not present in the state, that is the probability 0. So two things. One is that these are highly correlated state. That means if I know some information about the first qubit, I almost know every information about the second qubit because of this particular state. That's why these are known as highly correlated state or entangled state. So this is an important correlations or the important interference phenomenon known as entanglement. Now, general interference for that, instead of the CX circuit, we will have control unitary circuit, and accordingly, you can design the mathematical principle. I'm just showing. So suppose you apply the Hadamard gate here. So the first state will be plus state, and suppose second state, instead of starting with 0, I suppose start with psi, for example. Okay. And this is a multi-qubit control unitary operation, say for example, because this has something to do with quantum phase estimation algorithm as a building block. So I just make it bit detailed versions. Okay. So once you apply on this particular state in the second step as a controlled unitary instead of control X gate. So because the first qubit is 0, so it does nothing to the quantum state psi. So 0 psi will be intact. But when the first qubit is 1, then it will apply the unitary operation on the quantum state psi. So if the unitary operations I can write in the form 2 to the e to the power 2 pi I theta. So my state will become normalized 0 plus e to the power 2 pi I theta times 1 tensor product with psi, right? So this is like 0 psi. This state is 0 psi. You can write this way also. Earlier it was 0, 0 plus 1, 1. So 0 psi plus u psi, u1 psi. u1 psi. So these are equivalent basically. So now till this I can see I can create now interference, right? And immediately my probability instead of this 0.5 I can have three different probabilities. For example, I can create for 0, 0 basis I can have say a0 square. I can have 0, 1 basis I can have. So the probability instead of 0.5, I can have say a1 square. Then the second probability can be a2 square. Third can be a3 square, and so on, right? So I can create this kind of basically different probability in the histogram by using this kind of circuit. Now till this is a interference I create. Now if we apply the Hadamard gate after this, so this is another part of the circuit which actually you can apply in the step 3 to do something that is called the Hadamard test or expectation calculation. For many problem, we do the expectation of a particular observable, and this is the circuit for that. I'll have some details on this later. Okay. So this is like the second part is redundant for now, but later it will come. So in general, if I have quantum gates that will represent my quantum state vector, and these are the matrices which will represent the quantum circuit or the observable or the operators, right? Operators in general, right? The big all the gate operations together, because you are decomposing the gate from the unitary operator u, right? So this is the quantum states high where you encode your information. Then you apply a unitary matrix and you get an evolved psi prime, for example, and then you do the quantum measurement on top of it to get certain information, right? So this is the scenario how it works. So for example, the Bell state I just described, right? How it works. This is the Bell state circuit, the Hadamard and the C0 configurations, and you get the probability 0.5, 0.5. Now this is a quantum phase tree circuit, where I described the steps like 0, 0 to plus state, one size state, and then this particular state. And even if you just change the theta equals to 1 degree, then you get the probability of 0 to be 0.9999. Earlier it was 0.5, and the probability of 1 will be 7.6 10 to the minus 5. So how you manipulate the probability using certain control gate and gate operations. So this is an important example. So in general, there are sets of equations. Okay. One is the state vector for postulates. So where you represent your information in the quantum state, and the um, coefficient of the state vectors or the basis vectors, right? Should be square sum equals to 1 to satisfy the probability law. In general, the operators should be Hermitian operator, and there is an second postulate of quantum informations. That is, if there is an operator A associated with a particular eigenfunctions psi, it gives the desired quantity A from that particular wave functions, right? And this is the how to get the measurement postulate. From the measurement postulate, we get the probability outcomes from given a particular quantum state psi. If I have a projector PM, so this particular expectation gives the probability value of that particular quantity, right? So these things all are coming from the postulates, as well as for the state vector description, we know the time evolution equations, as well as the for density matrix, this is the von Neumann equation. So all these things are related with the quantum circuit generations part. Once you have the interaction picture, that means your quantum system is interacting with the environment, how much informations you lose, how much dissipations you do. So then these quantum open quantum system postulates are relevant. For example, the Lindblad master equations and cross operator form. So those who are interested in much more details of circuit component design, the circuit operator design, and related theory. So there are certain quantum tools in Qiskit. For example, the Qiskit quantum information tools, Qiskit circuit toolbox, Qiskit transpiler toolbox, how to optimize circuits, Qiskit primitive toolbox, how to do sampling and estimations job on a software platform. So these are various software tools available in Qiskit. So you can have a look. So in general, we divide a quantum circuit in three parts: encoding, evolution, measurement. That's it. Now, after this, you need to do the post-processing and classical part just to get your result has some meaning with your problem. This is another circuit called the swap test circuit, how you do the inner product on a quantum computer. So this is I'm keeping as a homework. Okay. The details will be available in the slide. The same thing, like stepwise, first state will be a superposition state. Then there is a C swap gate basically. If it is 0, there is nothing. The information will be psi-phi as it is. But if it is 1, the information will be swapped between these two states like phi and psi. So phi will be psi and psi will be phi if it is the 1. So this is the logic. And then again you apply another Hadamard. So ultimately this circuit will give you the inner product between two quantum states psi and phi. So this is the fundamental of quantum support vector machine, quantum SVM algorithm, quantum machine learning stuff. So those who are interested in Cardinal method, so this is an most important circuit for that. So so this you can study in depth. Okay, so when typically you have a theoretical U, time evolution operator, in general, theoretical U has infinity number of terms, so you need to try it up to certain order. There are certain approximation method for that, for example, tautorizations method. And what order of tautorizations you do, based on that you have a truncation error. Once you have an approximate unitary operator, you need to decompose that operator into basis gates, either Keck decompositions, Euler decomposition, or any in general Pauli decompositions you do. You have to route after this. You can simply do on the classical machine, classical simulator on the HPC. up to certain limits, say up to 40 qubit kind of applications, as an example. But if you want to do on a quantum computer, you need to match with the qubit topology of a quantum computer. That means these basis transformations further be decomposed into the basis gate of the quantum hardware QPU. And because it is QPU which involved, so there might be hardware noise, right, up to certain level. So you need to mitigate that, right? So this is the flow, how basically a circuit operates. So there is a second level of error will come in the quantum computer. So this is a topology map. So maybe I'll start from here because of lack of time. I'm stopping here. So I'll discuss about qubit topology, various family of QPU, and then I'll start certain quantum information theory stuff and some example. So with this, I'm concluding the sessions here for now, and you are open to ask any questions. Thank you very much.
Thank you so much, sir, for this wonderful session. I request all the participants, if you have any doubt, please write it in the comment, in the chat box.
So I'll be sharing the PPT tomorrow. Once the lecture is completed, I'll be sharing today's and tomorrow's both slides together, because that will be yet to ready tomorrow's thing. Projects and all is a bit difficult to provide as far as IBM is concerned, but there are lots of projects going on. For example, in chemistry, people are working on various energy calculations problem, ground state, excited states calculations. Physics people are trying to understand various um, renormalizations theorem, magnetic phase transitions and all. In engineering, there are lots of problem. People have been working on image processing, on some of the machine learning stuff. Especially it has recent applications and potentially quantum advantage application in quantum optimization techniques. For example, max cut problem, and also the kind of problem in the graph problem where you have a combinatorial optimizations problem. Can you map it on the quantum computer using formulations like QBO and all? So there are lots of problem, and it just I mean, you just need to put some time and then do some research. Yeah. IBM provides 10 minutes free for all the educators, right? Even yesterday there was an event for the students and the community, purely for how to use IBM quantum computer for the education purpose. So there is a free 10 minutes for everyone, those who are from the academic side, every month. And for a year, if you use regularly, there will be 180 minutes free for this. Now, if you have dedicated projects and all, so you need to contact the IBM persons for premium access and all. But for educational things, there are all the free resources are there. So, for example, let me share the Qiskit resource. So I'm sharing a basically website here in the chat box. You can go to this link. All the basics programming examples are there. How to install Qiskit, how to use write a simple Python code for certain, and there are some applications are also listed, so you can have a look. Oh, thank you. Yeah, future improvements. Yes, yes, sir.
Thank you, Dr. Mostafa. It was indeed a very great session, and I appreciate your efforts that you have completed all three lectures in one due to five, because it's not so easy to speak continuously for 3 hours. So thank you. I extend my gratitude on the behalf of EICT Academy as well as on the behalf of EICT Academy of IIT Roorkee, IIT Kanpur, and NIT Patna. We extend our heartfelt thanks to you. And tomorrow also you would be taking another three lectures from 2 to 5.
Yes, sir.
And after that, we will be concluding this FDP, because tomorrow will be the last day of this FDP.
Sure, sir. Thank you so much, sir.
So I request you to share the PDF files of your PPTs so that we can share it with our participants,
Yes.
as well as you can share 10 multiple choice questions for quiz for our participants.
Question I already shared with one of your TA, I think, your scholar, and those were very easy and questions. And PPT tomorrow I'll share together. It's fine, right?
That's fine. That's fine.
Thank you.
Okay, participants, we can now, if there is no more question, Ankita, is there anything you would like to have any announcement? Anuradha, are you there?
Yes,
Sir.
sir.
Yes, sir.
Any announcement?
Yes, sir. Announcement for the third quiz to all the participants and participants who have not attended quiz 1, quiz 2, they can also attend both the quizzes. The third quiz and all the three quizzes will be available till 31st of May, 11:59 p.m. So I request all the participants to attend the quiz in the particular period of time.
Okay, okay, thank you. Thank you, Ankita.
Yes.
Anything else?
Yes, sir. The score of quizzes will be no, sir. Okay. After all the quizzes, we will display the score. Okay. After the completion of the quiz, we will display the scores of all the three quizzes, and the best score from all the three quizzes will be taken for the certificate.
Yeah, best score out of those three quizzes will be taken as a final score, and on the basis of that, certificate would be given.
Yes, sir.
So, Ankita, done from your end?
Yes, sir.
Okay, that's good. So, all the participants, you may appear for the quiz 3 also, as mentioned by Ankita. And tomorrow we will be having another three lectures by Dr. Mostafizur Rahman, and then we will be